Let's now dig a little bit deeper into the Lorentz transformation. In particular, let's put some numbers here so that we get a little bit more familiar manipulating it, and then we'll start to get a little bit more intuition on how this transformation, or sometimes it's spoken of in the plural, the transformations behave. So let's pick the scenario in which our friend passes us by, and this is the same scenario we've been doing in previous videos, with a relative velocity, from my frame of reference, at half the speed of light. So the magnitude of her velocity is half the speed of light. She is moving in the positive x direction. And our space-time diagrams, they coincide at the origin. And so let's pick an event in space-time. And so let's say in my coordinate system, in my frame of reference, this event that we focused on in the last video, let's say that is at x is equal to 1 meter. X is, let me do that same color. X is equal to 1 meter. And let's say that time, or CT, is also equal to 1 meter. And like we said in, I think it was several videos ago, we could view this as a light meter, the time it takes for light to go 1 meter. So we will also say this is 1 meter. So in my coordinate system, in my frame of reference, this would be the point 1, 1. 1 meter in the x direction, 1 meter in the CT direction. Now, based on that, think about what would be the prime coordinates. What would be the coordinates in her frame of reference? And I encourage you to pause the video, evaluate the Lorentz factor using V and C, and then evaluate what x prime and CT prime would be. All right, I'm assuming you've had a go at it. Now let's work through this together. So first, let's figure out what the Lorentz factor. Actually, let's first figure out what beta would be. That'll simplify everything. So beta, let me do that blue color. Beta, in this case, is going to be equal to 0.5 c. That's her relative velocity in my frame of reference. The ratio between that and the speed of light. So that's just going to be equal to 0.5. You could just view beta as what fraction of the speed of light is that person traveling in the reference, or in my frame of reference, since we're using that as kind of the non-primed frame of reference. And so let's now think about what gamma is going to be, the Lorentz factor. The Lorentz factor is going to be, let me do it in that reddish color, not the magenta. It is going to be, so gamma is going to be 1 over the square root of 1 minus beta squared. Beta squared is, 0.5 squared is going to be 0.25. Actually, let me just write 0.5 squared just so that you see what I'm doing. So this is 0.5 squared. And if we were to evaluate that, let's see, this is going to be 1 minus 0.25. So that's going to be 0.75. So this is going to be equal to 1 over the square root of 0.75. 1 over the square root of 0.75. Let me get my calculator out. We can at least approximate it. So 0.75, let's take the square root, and now let's take the reciprocal of that. So approximately 1.15. So our Lorentz factor is approximately 1.15. And now using that, we can figure out what x prime and CT prime are going to be. X prime is going to be equal to my Lorentz factor, which is approximately 1.15. So maybe I'll write it as approximately going to be equal to 1, I'll do that same color, is going to be 1 point, I'm having trouble switching colors today, 1.15 times, now we're saying x is 1 meter, so x is 1 meter, minus beta. Beta is 0.5. So 0.5. And CT, we're also saying is 1 meter. So times 1. And then T prime, or I should say CT prime. CT prime is going to be approximately the Lorentz factor. 1.1. I always have trouble switching colors for the Lorentz factor. It's going to be approximately equal to 1.15 times, well, CT is 1. I think you see a little bit of symmetry here, and this one in particular because it had the same x and ct coordinates. So 1 minus beta, 1 minus beta, so 0.5 times x, which is, once again, 1. So times 1. And so in this particular case, it simplifies to half of the Lorentz factor, because this 1 minus 0.5 times 1, that's just going to be 0.5. And same thing over here, 0.5. So these things are going to be approximately equal to 0.5 times the Lorentz factor. We already had the Lorentz factor in my calculator, so let me just multiply by 0.5. And I get, it's approximately 0.5, I'll just say 0.58. So 0.58, 0.58. And once again, the units are in meters. So even though this is 1 meter and 1 meter, this over here, x prime, is 0.58, 0.58 meters, and ct prime is also 0.58 meters. So this is also equal to 0.58 meters. So one way to think about it, if right when right as she was passing me at x equals 0, time equals 0 in my frame of reference, I were to shoot my laser gun, or I were to turn my flashlight on, and that very first photon starts traveling, and so I could think about its path through space-time. It would look, that very first photon would look something like that. When I think that that photon has traveled 1 meter in the positive x direction and 1 light meter of time has passed, from my friend's frame of reference, she would say, no. At exactly that moment, let's say it hits an asteroid at that moment, it lights up an asteroid, she would say, no, that happened 0.58 light meters after she passed me up, and it happened 0.58 meters in the positive x direction. So something very, very, very interesting is going on. And I encourage you to think about what's actually going on with these different parts of the Lorentz transformations. The most interesting is what's going on, well, actually, it's all interesting. In fact, the symmetry is interesting. But the Lorentz factor, think about what's happening here. Think about what's happening here for low velocities, when v is a very, very, very small fraction of the speed of light. Well, then beta is going to be pretty close to 0, and then the Lorentz factor is going to be pretty close to 1. And think about what happens when v approaches the speed of light. Well, then this thing just booms. This thing gets larger and larger and larger as we see this denominator getting smaller and smaller and smaller. And if v were actually equal to the speed of light, well, then you're going to be dividing by 0. So that also all sorts of silliness starts to happen. So really encourage you to try out different numbers. We tried very high relative velocity, half the speed of light, incredibly high velocity. Try it out for something more mundane, like the speed of a bullet or something like that. But definitely get very familiar with this, and also manipulate it algebraically. In fact, maybe in the next video I'll manipulate this a little bit algebraically so that you can reconcile the way I've written the Lorentz transformation or the Lorentz transformations with the way that you might see it in your textbook or other resources.